Let's take a look at the test for divergence, which gives us a way to immediately check one thing about a series. It must pass this test to have a chance at convergence. So let me write down the statement and then we'll talk through it and I'll give you a logically equivalent way to think about what this test is saying. All right, so here's the test for divergence. If we have an infinite series, which I could write n equals 0, n equals 1. Let me just say n equals 1. The lower index here never will matter. If the series of terms of the form a sub n converges, then the limit of these terms that we're adding up is 0. This is a result that you may have anticipated if you've been experimenting with infinite series. Because if we're going to add up an infinite list of numbers and have it land on a finite number, eventually what we're adding up needs to get really, really small. Otherwise, the sum will keep changing as we go on and on in our series. So eventually we want to get to the point where we're adding up very small quantities that are not, taking us off course, if you will. So if a series is going to converge, the terms that you're adding together need to get very, very small. This is an if-then statement in mathematics. It's telling you if this is true, then this is true. You cannot read this backwards. It does not tell you if this is true, so if the limit of the terms goes to 0, then you get convergence. That is not true. The test for divergence never gives you the convergence of a series. It only might give you that a series diverges. So let me take this statement now. I'm going to reword it. So first, let me say that this is an if P then Q statement in mathematics. A lot of theorems are phrased this way in math. So if P is true, then Q is true. This expression is logically equivalent to something called the contrapositive. The contrapositive of an if-then statement is if not Q, then not P. This version of the test for divergence, which we're going to phrase now together, is actually the more useful version of the statement. So if not Q, then not P, when we look at the test for divergence, is if this limit is not 0, then you don't have convergence. And that's really what you're checking. So the best statement for the test for divergence is if the limit as n goes to infinity of a sub n is not 0, then the series diverges. And here I mean infinite series. This is what you check first when you look at an infinite series and you're trying to gauge whether or not the series converges or diverges. What you want to do is look at your terms here, take the expression that you're adding up, compute its limit as n goes to infinity. If the limit is not 0, because either it converges to something like 3 or it doesn't exist, there is no limit as n goes to infinity, you stop. The series diverges. However, if the limit is 0, then you just say the test for divergence doesn't tell you anything. Because if the limit is 0, you can't conclude anything. It might converge, it might diverge. Okay, so let's look at a few examples where we are going to start our analysis by taking the limit. So we'll analyze the limit of the series, and then we'll see whether or not the test for divergence applies. We have one kind of classic example, then I have two curveballs with trig functions. We will look at the harmonic series, which is a very famous series where the series diverges even though the limit is 0. And then I will give you a quick sketch of why the test for divergence is true. So I'll do a quick little proof. All right, for this first example, we are looking to add up terms of the form 4n over 3n plus 5. This is a nice application of the test for divergence because this series diverges If you take the limit of a sub n as n goes to infinity, that's going to look like the limit of 4n over 3n plus 5. This is a rational expression in terms of n. If you compare the highest powers on n, we get 4 to the n over 3 to the n, so this limit is 4/3, not 0. The test for divergence tells us that this series diverges. You have to be careful with the next two examples. I put them on here as a bit of a curveball because if you look at cosine of pi x and sine of pi x, if you picture the functions, cosine of x and sine of x, if you're just picturing cosine and sine waves and let the input or the argument into those trig functions go to infinity, you might say, hey, that bounces around. These oscillate, the limit does not exist. But actually, these are not the functions cosine of x and sine of x. These are very specific cosine and sine values. In particular, cosine of pi n, if you plug in n equals 0, that's cosine of 0, which is 1, whereas cosine of pi is -1, and then cosine of 2 pi is 1, -1, +1. So we get this infinite series of alternating ones and -1s. This doesn't add up to anything. And actually, if you look at every term, the terms are not going to 0. They're either 1 or -1. So the limit as n goes to infinity of cosine pi n does not exist. It's not 0, so we know this diverges. Again, you want to be careful, though, with these trig functions, because if you try to make the same argument with sine, or if you just say, hey, it's the same, it's not, because sine of pi n is 0 for every n. So this series actually does add up. It adds up to 0. Here is a famous example of how the test for divergence does not give you convergence. Because if you look at what we call the harmonic series, which is adding up terms of the form 1 over n, this series diverges, and yet the limit as n goes to infinity of 1 over n is 0. So you cannot apply the test for divergence in order to try to claim that this converges, because it doesn't. The test here just does not apply. There's a beautiful way to show that this series diverges, so I'd like to take you through the argument now. It's not only going to prove that this series diverges, but it's also a nice kind of exercise in pattern recognition. So as I write this down, I want you to try to follow how I'm choosing these partial sums and how we know what they add up to and the general statement that we can make. Okay, so the very first partial sum that I would like to write down is the first one. S sub 1 is just the first term in this harmonic series. I'm indexing here from n equals 1, so the first term is 1/2. The next partial sum would be S sub 2, 1/2 plus 1/3, but I want to skip that one and go straight to S sub 3. S sub 3 would be the sum of the first 3 terms, so that's 1/2 plus 1/3 plus 1/4. What I'm going to do is leave 1/2 alone, but take both of these terms that we've added compared to the previous partial sum and lower them down if necessary to 1/4. So I want to lower them down to this one. So this would be great. How about greater than or equal to 1/2 plus 1/4 plus 1/4. And the nice thing about changing 1/3 to 1/4 is that this is easier to add up. That's one of the nice things. So 1/2 plus 1/2, these two things together add up to 1/2, is 1. So I know that S sub 3 is greater than or equal to 1. Now the next partial sum would be S sub 4, and that would add up through 1/5. Then I would add up through 1/6, 1/7. Let's go to the one that adds up through 1/8 next. That is the seventh partial sum. S sub 7 would be this plus 1/5, 6th, 7th, and 8th. Started thinking about 1/6 and I wrote 6. Okay, so the next one is 1 over 6, then 1 over 7, and 1 over 8. Okay, let's stop for a second and just do a little pattern recognition. Let's make sure I've identified this correctly as the 7th. Notice from 1 to 2 went from the subscript here to the highest denominator, 3 to 4, so 7 to 8. Okay, so we're doing this right. Now I'm going to take these two terms, just like we did on the line above, and lower any terms as needed down to this lowest one, 1/4. Next, let's group together all 4 of these terms and lower all of the ones that need lowering down to 1/8. So we always want to go to something that looks like 1 over a 2 power. Okay, so when we do that, we can say that S sub 7 is greater than or equal to a half plus a fourth again, and now plus 1/8, 1/8, 1/8, 1/8. And again, the nice thing about this is that together, this is a half, this is a half, and this is a half because we have 2/4 and 4/8. So overall, this is 3 halves. I would like for you now to identify what the next partial sum of interest is. It's not going to be S sub 8, it's not going to be S sub 9. What's the next one that we would write down to follow the pattern that this argument is constructing? So identify what terms we need over here, what the subscript should be, and what they should add up to over here, what this lower bound for our relevant partial sum would be. Okay, here's what I hope that you wrote down. Notice each of the sums that I've identified ended with 1 over a 2 power. So we had 2, 4, 8. The next one would be 16. Okay, so that means that the partial sum of interest would be 1 lower than 16. It would be 15. So we would write down S sub 15. I'm not going to write out 15 terms. I definitely don't have room for that. But let me write out what we would group together over here. We would have all of this. So we would have and let me go ahead and do the greater than or equal to. Okay, so we would replace all of our terms with expressions that look like 1/2 plus 2 copies of a 4 plus 4 copies of an 8th. And then we would add to that 8 copies of 1/116th. So all of the terms 1/9, 1/10, 1/11, 12th, 13th, 14th, 15th, we would replace them with 1 over 16. When we do that, we've got the 3 halves that we had before, but now we're picking up an extra half so that S sub 15 is greater than or equal to 4, or sorry, 4 halves, which is 2. Okay, 2. All right, let's make a pattern now out of these lower estimates that we have for our partial sums. Notice that the 1/2, 3 halves are fractions. We have 1 and 2 here. Might help spot the pattern if I take 1 and replace it with 2 over 2. And if I take 2 and replace it with 4 over 2, I want to give like a recipe for the partial sums of interest. Okay, and then what might be the relationship between the numbers 1, 2, 3, 4 and the numbers 1, 3, 7, 15? If you struggle to make the connection between these numerators and these subscripts, try instead to connect these numerators 1, 2, 3, and 4 with this number down here, which we know is a 2 power. So 2, 4, 8, and 16. Let me give you a second to see if you can write down a formula, say in terms of k, that would link a subscript here, written with k, with this lower bound, written with k. Okay, so see if you can kind of generalize what the general partial sum of interest would be in terms of an index k. Again, the point of this exercise is just to practice pattern recognition and also trying to describe a pattern. Once you spot that there is a pattern, how do you start quantifying the terms in that pattern? Notice that this is 2 to the 1, and this is 2 to the 1 minus 1. This is 2 squared. This is 2 squared minus 1. This is 2 cubed. 7 is 2 cubed minus 1. So let me say that this is S sub 2 to the 1 minus 1. This here is S sub 2 squared minus 1. This is S sub 2 cubed minus 1. And this is S sub 2 to the 4th power minus 1. Okay, so we can write these subscripts 1, 3, 7, 15 as 2 to the 1 minus 1, 2 squared minus 1, 2 cubed minus 1, 2 to the 4th minus 1. Then look at, you can look at the terms. I think we can pass immediately to talking about these numerators here because this power on 2 is the numerator. So I've got 1 over 2. Here I've got 2 over 2. Here I've got 3 over 2. Here I've got 4 over 2. So that was the motivation behind converting the whole numbers 1 and 2 to their fraction forms 2 over 2 and 4 over 2. So what we can say is that in general, s sub 2 to the k minus 1 is, it's really greater, but I'll write greater than or equal to k halves. Okay, so that summarizes these partial sums of interest that we were able to do this neat trick on. Now, here's the thing, is that we would keep writing partial sums forever because this is an infinite series. So we have to let k go to infinity so that these subscripts can get arbitrarily large. But as k goes to infinity, what we're saying is that these partial sums themselves are unbounded. They grow without bound. So this series must converge. So this goes to infinity as k goes to infinity. So that concludes the proof that the harmonic series diverges. Now let me verify with a pretty fast proof that the test for divergence must be true. We are going to prove the first version of this statement, which said that if the infinite series converges, then the limit of the terms that you're adding up must shrink to 0. So that will be our hypothesis that I'm going to build the proof off of, that the series converges. My proof will begin with, suppose that the series adds up to some number s. So suppose this infinite series, which I'll index from 1 to infinity, converges to s. Here I'm just calling it s for sum. Then notice that the limit of a sub n, the limit that we're interested in, let me pause here. With my hypothesis that the series adds up to something, adds up to a number I'm calling s, I want to now prove that the limit of this term, a sub n, these terms that we're adding together, must go to 0. Once I've shown that the limit is 0, we're done with the proof. Here's what I'm going to do, is take this nth term and recognize it as the only thing different between the n minus 1th partial sum and the nth partial sum. In fact, let me write this. I think I'll write that description twice. So how about the limit as n goes to infinity of the partial sum going from, oh, I have to be careful here because I've got n, I want to add up, sorry, I think I'm overusing the letter n here, because if I want to say the nth partial sum, that means I need to stop adding when I get to the number n. So let me index now using the letter k. I'm just switching from n to k here to say that we're going to add up a1, a2, a3, a4, all the way through a sub n. This minus the sum where we add up from the first term to the n minus 1th term. If you compare these two sums and take their difference, the only thing that doesn't get canceled is the last term that we add up in this first expression, which is a sub n itself. We named this the nth partial sum. This is the n minus 1th partial sum, so I'm going to rewrite this just using that notation. So this is the limit as n goes to infinity of s sub n minus s sub n minus 1. Okay, so two partial sums. The thing is that we have a very, very powerful hypothesis here. We are imagining from the start that we are looking at a convergent series. So we know a lot about how this series behaves. In particular, I know that my partial sums tend to s as n goes to infinity. That's true for both of these expressions because as n goes to infinity, we're saying look farther and farther out in your sequence of partial sums, whether we call it s sub n or s sub n minus 1. These both subscripts, if you will, are going to infinity. So this is going to s, this is going to s. This limit is s minus s, which is 0. And that concludes the proof. So we can say that the terms a sub n have a limit of 0 as n goes to infinity. Again, notice this proof doesn't tell us that we can read the statement backwards. So the test for divergence is really truly a test that you can only apply if you want to check that a series diverges. And if the limit is 0, at that moment you cannot make any statement whatsoever. The only thing you could say is, hey, this might converge, it might diverge. So the test for divergence, be careful that you apply it correctly. It can only be used to verify that a series diverges.